Hello everyone, and welcome back to C++ Real-Time Audio Programming with Bela. We're picking up after a summer hiatus with a series of new lectures covering some exciting topics in synths and real-time audio effects. Specifically, today we'll pick up where we left off with the creation of state machines to implement the attack-decay-sustain-release, or ADSR envelope. This is a very common building block of modular synths. Over the course of this lecture, we'll learn what the ADSR envelope does and how to implement it using the state machine concept. We'll implement the ADSR with both linear segments and exponential segments. We'll implement this as a C++ class which we can reuse inside of our projects. By the end of the day, you'll have a working example using an ADSR envelope controlled by a button. As always, you can find the companion materials for this lecture on the GitHub link at the bottom of the screen. You'll need a Bela starter kit or a Bela mini starter kit to run these examples. For today's lecture, you'll also need a breadboard with a button and a resistor to trigger the envelope. Let's start with a review of where we left off. The finite state machine is a simple mathematical model of computation which is really useful for a wide variety of interactive systems. There are essentially four requirements to implementing a state machine. First, we need a set of states that the system can be in. Second, we need a set of transitions to move between those states. Third, we need a set of inputs, such as sensor data or timing, which determine which transitions should take place and when. Finally, the system should generate a set of outputs depending on which state it's in. The state machine should have only a finite number of states, and should always be in one and only one of these states at any given time. The behavior of a finite state machine should also be deterministic. We should be able to determine exactly which transitions would take place based on the available inputs. For a more detailed overview of the state machine concept, see the previous lecture. Last time we also looked at how to practically implement a state machine in code. We saw that we needed one or more variables to keep track of which state we're in at any given time. These were typically global variables so that their value would be remembered across calls to render. In this simple example, we have a variable called gState, which is a global variable which starts at a value of 0. In our code, we also needed a set of if statements to check which state we were in. These would typically be inside of our render function, where we would undertake different behaviors depending on which state the system was in. In this example, we check for a series of different values of gState inside the render function. Each value would have a different set of actions and transitions associated with it. A useful implementation trick we saw last time was to give the states names rather than numbers. This doesn't change the behavior of the program, but it makes the code easier to understand. We define constants at the top of the file which associate each number with a name. The enum keyword in C and C++ was particularly useful. This stands for enumerate, and it's a simple way of defining a lot of constant values all at the same time. In this example, we define kStateOpen to have a value of 0, and then each subsequent state has a value 1 higher than the previous one. Therefore, when we define gState, rather than assigning it a value of 0, we assign it the name kStateOpen, which is completely equivalent. And inside of our function, which checks for what state we're in, we also check for the names rather than the numbers. Implementing the state machine also requires a further series of if statements, which are going to look at the inputs to the system. The inputs will determine which transitions take place between states. The idea is that we'll first look at what state we're in, and once we've done that, we'll use the if statements to check the inputs and decide whether a transition needs to take place. If no transition takes place, then what happens is what's called a self-transition, which means that we end in the same state that we started in. This may in fact be the most frequent event in most interactive systems. In this example, we first check what state we're in. If we're in the state kStateOpen, then we first generate an output using the function motorOff. We then use a further if statement to check whether the button was pushed. If the button was pushed, then we need to transition to a different state. On the other hand, if we're in the closing state, then there might be a different set of actions and a different set of transitions that could take place. Notice here that changing the state is very easy. All we need to do is assign a different value to the global variable gState, such that next time we run this code, we'll be in a different state and a different set of code will run. Finally, from a practical point of view, we need some clear planning on when it is that we're checking for transitions. If we're implementing state machines in digital hardware, we'll often have a clock signal that tells us when to check the inputs and generate transitions. On the other hand, in the context of real-time audio, such as on Bela, we might use the audio frame clock for this purpose. Each audio frame will check what state we're in, will check our inputs, and will generate any outputs and transitions accordingly. This will take place inside the for loop in the render function. We might also need to think about when our actions should take place. Some events will happen only once on entry to a state. Other events might happen every single frame as long as we remain in the state. Again, this is just a brief overview. There are more detailed examples of state machines in the previous lecture. We're going to move on now to talk about the ADSR envelope. We previously saw some simple examples of linear and exponential envelopes. By contrast, the ADSR is a more complex envelope. It has 4 segments called attack, decay, sustain, and release. These segments are designed to simulate the amplitude profile of many acoustic instruments. If we're implementing an ADSR envelope, we're always going to be in one of 4 phases, or states. Again, these states are the attack, decay, sustain, and release states. In the attack state, the level of the envelope will rise from 0 up to a maximum value, which we typically normalize to 1. In the decay state, the level will drop from 1 to some predefined sustain level. Then, in the sustain state, the level will remain constant until we move to the release state. At that point, the level will drop gradually to 0 over a specified period of time. So as you can see, there are 4 segments involved in implementing an ADSR. These can either be linear segments or exponential, and we'll see both in this lecture. An ADSR generator will typically have a number of parameters that can be adjustable. These include the attack time, the decay time, the sustain level, and the release time. The attack time, decay time, and release time all control how long the envelope spends in that particular state. Typically, the attack time and the decay time will be quite short, and the release time may be a bit longer. The other parameter is the sustain level, which indicates what level the output should be held at in the sustain state. This will typically be a value between 0 and 1. In a typical implementation of the ADSR, the attack phase of the envelope will be initiated by a note onset, for example, a key press. The envelope will proceed through the various states, and it will remain in the sustain state until a note release event is received. We'll come back to this progression of states momentarily. But meanwhile, let's back up a couple lectures and refresh our memory about creating line segments. A line segment is a function that has a constant slope over time. We might express this in continuous time as v of t is equal to a times t plus b, where a is the slope, b is the intercept, and the segment is defined between some time values t1 and t2. To reformulate in a more common way that we see in real-time implementations, let's consider a segment which starts at a value of b1 at time 0 and then goes up to a value of b2 by time capital T. We can therefore work out the equation as shown here. The slope is b2 minus b1 divided by capital T, and the intercept, where the segment starts, is a value of b1. Notice that what we're doing is very similar to what the map function does. We're essentially creating a linear mapping between time and output value. Let's rewrite this now as a discrete time function that can be implemented in a digital system. We here have an expression for v of n, which is essentially a sampling of the original continuous function v of t. We need to ask ourselves how to implement this line segment in real time. We can look at this graph and we can see what needs to happen over time, but what we do in the moment, each individual audio frame, needs a little more thought. We need to think about how we get from frame n to the next frame, n plus 1. We can rewrite the above equation recursively as v of n plus 1 is equal to v of n plus the slope, which is b2 minus b1 over capital N. In other words, we're adding a constant increment each frame until we reach the desired endpoint. In Lecture 12, we made a C++ class to encapsulate the ramp generator. It had 2 key methods. One of them was called ramp2, which indicated a value to go to and the amount of time to take to get there. We also had a method called process, which we called every single audio frame to return the next value in the line segment. The idea was that once we reached the end of the segment, the value stayed put until we called ramp2 again. We had a couple additional methods, one which caused the output to jump to a particular value, and another method that we could use to query whether the ramp had finished or not. All of this is described in more detail in Lecture 12. Let's now look at how we can implement an ADSR as a state machine. First of all, how many states do we need? The answer isn't 4, but rather 5. We need states for attack, decay, sustain, and release, but we also need an off state in between instances of the envelope. Now, which transitions should be possible between these states? For the most part, this is going to be implemented as a cycle. The off state goes to attack, attack goes to decay, decay goes to sustain, and sustain goes to release, and then finally the release state goes back to the off state. Sometimes there are some other transitions possible. For example, we could go from the release state or the sustain state directly back to the attack if there was another note onset during that time. Next, what inputs do we need to know when to change state? We need, at minimum, note onsets and releases and some way of measuring elapsed time. In this example, a note onset will take us from the off state to the attack state. A measurement of time will take us from attack to decay. Likewise, a measurement of time will take us from decay to sustain. In the sustain state, we remain there until we receive a note release event. Then we move to the release state. The release state will also go back to the off state after a specified period of time. On the other hand, you can see that there are two possible transitions out of the release state. If we receive a note onset before the release time has elapsed, we'll go straight back to the attack state. Finally, what outputs does this state machine need? Mainly, we need to create line segments to generate the envelope. In the off state, the output should always be 0. Each of the other states will be either a ramp or a constant value. So in the attack state, we'll go from 0 to 1, the decay state will go from 1 down to the sustain level, the sustain state will hold a constant value, and the release state will ramp down to 0. A variation of this is when in the release state, if we receive another note onset message, we might want the ramp to start where we left off and ramp back up to 1. Now let's look at each individual state in more detail. First, we have the attack state. The attack state is entered on a note onset message. Its behavior is to create a linear ramp from the starting value to the final value of 1.0. We saw in a previous slide the formula that we need to implement this ramp. So here we have a value of b2 is equal to 1.0. b1 might have a value of 0 if we are coming from the off state, or it might have a different value if we were coming from the sustain or release states. The duration of the ramp, which is given by a number of samples, capital N, is dependent on the attack time parameter. When we enter the attack state, we ought to calculate a value of the increment, which we're going to add to the output each individual frame. That value is given here, b2 minus b1 divided by capital N. All of this is implemented inside of the ramp class that we made before. Next, let's look at the decay state. The decay state is entered when the ramp reaches 1.0 in the attack state. The behavior of the decay state is to have another linear ramp which goes downward from 1.0 to the sustain level. The duration of this ramp is given by a number of samples determined by the decay time parameter. Once the decay time elapses, we'll move onward to the sustain state. As before, we'll need to calculate the value of the increment on entry to this state. That increment will then be added to the envelope value each successive audio frame. The sustain state is entered when the ramp reaches the sustain level in the decay state. We don't have to do very much in the sustain state. All we need to do is hold a constant value of the sustain level. We wait for a note release or note off message, which will tell us to move onward to the release state. What this means is that we also don't particularly care about elapsed time in this state. We don't need to count samples, we only need to wait for the release message. In some implementations, it's possible that we might get a second note onset while we were in the sustain state. In that case, we might consider implementing a transition from the sustain state directly back to the attack state. Finally, we have the release state. This is entered when a note release message is received. Its behavior is similar to attack and decay in creating a linear ramp. In this case, the ramp starts at the sustain level and goes downward to 0 over a duration given by the release time parameter. During the release state, if we receive another note on message, we should go directly back to the attack state. As before, we need to calculate the increment value when we enter the release state, and then we add the increment to the envelope value each successive audio frame. When the ramp reaches a value of 0, we should then go to the off state where we wait for a note onset message. We're now in a position that we can implement the ADSR state machine. In the companion materials, you'll find an example called ADSR, which has partly implemented the structure for you. You'll need to finish implementing the ADSR state machine using a button to trigger and release the notes. A button press should cause a note on event to happen, and a button release should cause a note off message to happen. The output of the ADSR should control the amplitude of the output. The parameters of the ADSR are given to you in sliders that you can control from the browser-based GUI. You can see that the states have been defined for you already in an enum statement at the top of the file. You'll need to implement the code inside of render, checking which state you're in and implementing different behaviors accordingly. To implement the line segments when the states change, you can use the method ramp2 inside the ramp object. Here you can see the wiring diagram for hooking up a button with either a Bela or a Bela mini board. Notice that this example has a pull-up resistor to 3.3 volts, while the button connects between the input and ground. That means that when the button is pressed, we should read a low value at the digital input, and when the button is released, we'll read a high value. Build this circuit, and then go to the code in the ADSR example and implement the state machine. This example uses the Bela oscilloscope to show you the output signal and the value of the envelope, so you can open the Bela oscilloscope to see if your example is working as expected. Pause the video here and try it. Alright, here we are in the completed ADSR project. You can see that we're using several classes. We're using one called wavetable, one called ramp, and one called debouncer. These are defined over here in C++ and header files. You can open them to inspect them if you want. The ramp class is the one that implements the line segment that we've discussed. Wavetable we've seen in an earlier lecture. This implements a wavetable oscillator, and the debouncer class is a simple way of debouncing the push button, which we looked at in the lecture before this one. We're reading the button on pin number 1, we are defining objects for each of those classes, and we're using the browser-based GUI and the oscilloscope in this class. So here then we have the states defined in this enum statement. So the way this works is that k ADSR state off is equal to 0, then this will be equal to 1, this will be equal to 2, 3, and 4. But remember, once we define these states as names rather than numbers, we should always use the names and never refer to the numbers. This makes our code more readable and consistent. This global variable, GADSR state, keeps track of which state we're in, starting with the state of off. The setup function has some initialization for the wavetable, the ramp, and a few other things. Nothing to change here, so I won't go through it in detail. This brings us then to the render function. At the beginning of the render function, we're gathering all the values from the GUI sliders, as we've seen in previous lectures. We're setting the frequency of the oscillator based on the frequency we read from the sliders, and then we have our typical for loop, which steps frame by frame through each of the audio frames. Inside the for loop, we are reading the value of the button with the digital read function. So we pass it the Bela context, we pass it which frame we are reading, and we pass it the value of the button pin, which was pin number 1. And then we're using this debouncer class to tell us whether the button is pressed or not, but remove some of the natural bouncing of the metal contacts. Remember that the button is wired such that pressing it results in a low value, and that's why the note on variable is equal to the inverse of whether the button is pressed or not. Here then we get into the state machine itself. So you can see that we have a series of if statements. If GADSR state is equal to off, then we do one thing. Else if we're in the attack state, we do a different thing. Else if we're in decay, we do something else. Else if we're in sustain, we do something else. Else if we're in release, we do something else. And then within each of these if statements, we can check our inputs and generate our outputs. For example, in the state off, we are looking for a note on message. That is to say, we're looking to see whether the button is pressed or not. If it's true that the button is pressed, then we set our state to the attack state. So this is a transition that's occurring here. By setting the value of GADSR state is equal to k ADSR state attack, that means that the next time around the render function, it will end up in this block of code rather than this block of code. The other thing we're doing when the button is pressed is we're telling the ramp to ramp from wherever it is at the moment to a value of 1.0 over the amount of time specified by attack time. This came from the GUI sliders. Next up, if we're in the attack state, what we need to do is check whether the ramp has finished or not. So we're going to use this method of gramp called gramp.finished, and that's going to return a bool, true or false, depending on whether the ramp is done. If it's finished, then we're going to have a transition to the decay state, and then while we're transitioning to the decay state, we're going to create another ramp, this time going from 1.0 to the sustain level over the amount of time specified by the decay time. Next up, inside of the decay state, we are also looking for the ramp to have finished. When it's finished, we're going to change the state from decay to sustain. Now notice that there's nothing else that we actually need to do here. The ramp has reached the sustain level and it will stay there until we tell it to do something else. That's exactly the behavior we want. Next up, when we're in the sustain state, we want to be looking for a note off message that tells us it's time to release. So here we have that variable note on, and we can look for it having a value of 0 or false. So if not note on, Then we're going to create a transition to the release state, and we're going to tell the ramp to ramp down to a value of 0 over the amount of time specified by the release time. Finally then, if we're in the release state, then the ramp is busy going downward towards 0. We're going to check if it's finished or not. Has the ramp reached 0? If it has, we'll change state to be in the off state. But meanwhile, we might also get another note on while the ramp is still releasing. So we're checking for that here. If there's a note on message, then we're going to transition back to the attack state, and we're going to have the ramp go back up from wherever it got to a value of 1.0 over the attack time. Then the last thing that we had to add to our code was we had to use the value of the ADSR envelope to scale the output. So this is the line that changed. Float amplitude is equal to gramp.process. Notice that it's the ramp object that's actually keeping track of what the value of the envelope is at any given time. The state machine is telling us where it should be ramping to under what circumstances, but by getting the current value of the ramp, this is what's going to give us the amplitude, which we then multiply by the wavetable oscillator in this line. We write that to the audio output, and then we log to the scope two things. First of all, the audio output, and second of all, the amplitude of the envelope. So let's run that and give it a try. Okay, and with this project running, we can open the Bela oscilloscope. And we should be able to see that when we press the button that we get an envelope. Now, if we zoom out the timescale, we'll be able to see the segments a little bit better. So I'll go to the controls here, and we're just going to zoom out until we get something more like, I don't know, 52, let's say. So there you can see the different segments of the ADSR. Now, another thing that we could do to make the plot a little bit more stable would be to set the trigger on the oscilloscope. So we could set the trigger to be on, let's set it to be on channel 2. This is the value of the envelope and not the value of the audio output. And we're going to set it to be a level of, I don't know, say 0.07. Something a little bit greater than 0, and we're going to set the mode from auto to normal, which means we're only going to redraw the screen when this trigger happens. So now, you can see that it holds the screen fixed, and we can always see the attack and decay states. If I press this really quickly, you can see there each of the segments: attack, decay, sustain, and release. We can also adjust the controls for this by using the browser-based GUI. So for instance, if we wanted to have the attack time be a bit shorter, maybe the decay time could be a bit longer, sustain level higher, and a longer release time. We can go back to the Bela oscilloscope now and there we go. So we can see each of the line segments in the ADSR envelope adjustable by the GUI. In the next part of this lecture, we're going to encapsulate the ADSR into its own class so we can reuse it easily in different contexts. We'll follow the convention we've used with other audio classes, where we define a method called process, which we expect to call once every audio frame. This method will return the next sample of the ADSR regardless of which state it's in. It will also cause the envelope to advance its value and potentially change state, for example, from attack to decay or decay to sustain states. We'll also need methods to trigger and release the envelope. We're going to implement these as methods rather than passing sensor data directly into the class, so that it's very easy to use the ADSR in different contexts, and we don't make assumptions about what kinds of sensors might control it. The method called trigger will cause the ADSR to move to the attack state from whatever state we're currently in. Conversely, the method called release will cause the envelope to move to the release state from whatever method we're already in. Typically, release would only happen from the sustain state, but in certain edge cases it might be useful to be able to release the envelope from any of the states. We're also going to need methods to set and get the value of each of the parameters. One example of this is the method called setAttackTime. We pass in a time in seconds which indicates how long the attack state should last. This will be converted to a number of samples for the purpose of calculating the increment in the attack state. We'll put a ramp object inside the ADSR class to implement the line segments. The ADSR class should involve most of the code that you previously had inside of your render function, but it's going to have to be moved into process and into other methods of the class. We can declare the different states that we might be in inside the class itself rather than at the top of the render file as we did before. The idea of doing all of this is that it's very easy then to make multiple ADSR objects within a project. For example, it's very common in modular synthesis for the filter cutoff frequency to have an ADSR on it as well as the amplitude. This brings us to our next task. In the project called ADSR class, you'll find the class declared inside of the file adsr.h. You can see there the definition of the parameters and the methods. Your task is to implement the methods inside of the file adsr.cpp. There will also be some code to implement inside of render.cpp, which uses the ADSR object to control the amplitude of the waveform. Once you have this class-based implementation working, then you can make a second ADSR envelope which you're going to use to control the filter frequency. Remember that you're going to need to renormalize the output value of this envelope. The filter frequency shouldn't be a value between 0 and 1. It needs to be a reasonable range of frequencies in the hundreds or low thousands of hertz. You can use the filter class to implement the resonant filter, as we saw in lecture 12. If you'd like, you can also implement a separate set of parameters in the GUI to control the filter ADSR versus the amplitude ADSR. Once you've done all that, you can experiment with different sounds by changing the different settings of the ADSRs. Pause the video here and try it. Alright, here we are in the class-based implementation of the ADSR. We're going to start in the file adsr.h. This file was provided for you, and it contains all of the structure of what your ADSR needs to implement. So you can see here that the enum statement defining the different states is actually inside of the ADSR class. Here I've taken the K prefix off of the states just as a matter of style. One reasonably common convention in a C++ class is for constant values to start with a capital letter without a prefix. Again, this is a matter of coding style, it's up to you. Here we have the methods that the ADSR class implements. We have a constructor, two different versions of it, one of which provides a sample rate. We also have a method for setting the sample rate. And then we have our trigger and release methods that we saw on the slides. This should start the envelope, and this one should move to the release state. The process method is very important, of course. This is what calculates the next sample of the output, returning it to the caller. This will also be responsible for changing the state of the ADSR as needed. We also have this method isActive, telling us whether or not we are in the off state effectively. We have some methods for getting parameters and setting them, and then we have a destructor. And then finally down at the bottom we have the state variables that we need to keep track of across the class. Here notice that the state of the ADSR is not a type int, but is actually type state with a capital S. That is a special type that's been created here in this enum statement. Basically, it's a fancy way of saying that the only valid values of this variable are those that are defined inside of the enum. You could equally well use an int for the same effect, but this is slightly more robust to accidentally writing bugs. We also have our ramp object inside the ADSR class, and this is what's actually going to handle the values of the output. Going across then to adsr.cpp, we can start with the process method. You can see that a lot of the structure is the same as we saw before. We have a series of if and else if statements that are checking which state we're in. We have a slightly different coding style here with the names of the states and the underscore after the instance variable, but otherwise the same thing is going on. In the off state, we're actually not doing anything because we're going to wait for the trigger method to be called to move us to the attack state. Inside the attack state, we're going to be looking for the attack ramp to have finished. This is very much like what we saw before, where then we call ramp2 to ramp from 1.0 down to the sustain level over a period of time given by the decay time. When that ramp finishes, we find ourselves at the decay state, where again we're going to have a ramp running. When that ramp finishes, then that means that we have reached the sustain state, and we will change our state accordingly. This again is basically all the same code as we saw before, just now encapsulated inside of this class. In the sustain state, we don't actually have anything to do here. We'll just wait for the release method to be called, which will change the state to the release state. Once we get into the release state, then there will be a ramp going from whatever value we started at down towards 0. When that ramp finishes, then that's our sign that we should transition to the off state again. At the end of this process method, we have to return the current value of the ramp, which is the output of the ADSR envelope. Now let's look at the trigger and release methods. The trigger method is here. This is going to be called externally, for example, from the render function, when a note on occurs. The trigger should do the things that we saw before to get ourselves from the off state into the attack state. We're going to set state is equal to state attack, and we're going to call ramp2 to ramp to a value of 1.0 over the amount of time given by attack time. The same idea applies with the release method. We're going to set ourselves into the release state, and we're going to call ramp2 to go down to a value of 0.0 over the release time that was specified. Then finally, we can look at the get and set methods here for setting each of the parameters. You can see that what we need to do for set attack time is we take this argument and we basically store it inside of the instance variable attack time. So notice the convention of using the underscore to indicate instance variables is sort of handy because it differentiates our own copy of attack time inside this class from the argument with almost the same name. The other thing that these methods let us do is that it lets us sanity check the arguments. For example, we can't have a negative attack time. We make sure that the attack time is always greater than 0, and if it's not, we set the attack time to 0. And the same idea applies with the rest of the methods as well. So we check the decay time, the sustain level, and the release time. Let's now go to render and see how this is used in context. In this particular example, I've implemented the entire stack of things described in the slide. In addition to using an ADSR for amplitude, I'm also using another ADSR object to control a filter. So this project also implements a filter class, which implements a resonant second-order filter based on a previous lecture. We can see here that we have two different ADSR envelopes. They're called G-amplitude ADSR and G-filter ADSR. This really brings home the reason why the class is so convenient. We don't have to duplicate hardly any code at all. All we have to do is create two objects. Inside the setup method, the main change is that I've added a further series of sliders to adjust the sensitivity and parameters of the filter ADSR as well as the amplitude ADSR. Then inside of render, we have to get some of those parameters from the sliders, and then we have to set them inside of the ADSR objects. So notice here we're calling things like set attack time, set decay time for each of G-amplitude ADSR and G-filter ADSR. We can do all of this once at the beginning of the render function because we know the sliders will never change value once we're inside of the render function. Then we have our for loop. This counts through the number of audio frames as usual, and we are, as before, going to call gdebouncer to process the value of the button. Now, I'm using a couple other methods of debouncer in this particular project which tell us whether there was a falling edge or a rising edge of the signal. What this tells us is, was the button pressed just now, or was the button released just now? And if that's the case, if the button is just pressed, we're going to trigger each of the ADSRs. If the button was just released, we are going to release each of the ADSRs. This is as opposed to getting the current value of the button. Getting the value from the amplitude ADSR is relatively straightforward. We call its process method, and we store the result inside of this variable called amplitude. We can do exactly the same thing then with the filter ADSR, and we are going to store it in this variable called filter control. Now, notice I'm calling this filter control and not filter frequency because technically what comes back from this envelope is not yet a frequency. It's a normalized value between 0 and 1. And if we want to scale it to a sensible range, we're going to have to multiply it by the sensitivity that we got from the sliders and add to it the base frequency of the filter. So then we can call gfilter.setFrequency and set the filter frequency according to that calculation. We're going to calculate the output of the oscillator, scale it by the amplitude similar to before, and then pass it through the filter. I'm multiplying this by 0.5 here just because it's a resonant filter and it can create a bit of a peak and we don't want any clipping on our output signal. Finally then we can write the audio to the output and each of the ADSRs to the oscilloscope. Notice we have 3 channels on our scope now, not 2, because we have the audio output, the amplitude ADSR, and the filter ADSR. So with that, we can run it and see how it works. All right, and let's open our oscilloscope as before. Press the button. So first of all, you can hear that the sound is richer than it was before because now we have a filter whose frequency is changing. Let's again zoom out the screen so that we can see the envelopes a little bit more clearly. So I'm going to zoom these out to a greater amount of time resolution, and then I'm going to change the trigger from auto to normal and set this to be slightly greater than 1. We'll trigger on the amplitude ADSR as before. Now we can see it. So you can see in the blue the amplitude ADSR and in green the filter ADSR. Notice that the filter opens up more slowly than the amplitude. This gets a sort of brassy sound in classic analog synthesis, and it's something you can experiment with. You can open the browser-based sliders to change some of these parameters and see what they sound like. And let's just make one change just to see how it sounds. Let's turn the waveform down to a lower frequency. We will have a faster attack, a faster decay, maybe a higher sustain level, a longer release. Let's also turn up the filter release time. Let's say, let's make it a little bit faster than the amplitude release. Can turn the filter Q up a bit, and we'll make the filter attack time even a bit slower, decay time a bit slower, and maybe a lower sustain level. Let's just see what that sounds like. So there you go. You can experiment with these parameters and get a variety of different sounds. In the final section of this lecture, we're going to implement the ADSR not with linear segments, but with exponential segments. There's two reasons to do this. One is that traditional analog ADSRs would oftentimes use first-order filters to implement the segments. These produce exponential rather than linear rises and decays. The other reason is that human hearing is logarithmic in nature, such that an exponential decay produces a more realistic effect of a constant drop in loudness. Now, our question is, what information do we need to implement one single exponential segment? We need to know where we're starting, we need to know where the segment is ramping up to, and we need to know the time constant, which indicates how fast or slow the segment changes. Reviewing Lecture 12, recall that an exponential envelope is one that gets smaller over time by a constant percentage of its value, rather than by a constant slope. This envelope is a good simulation of the amplitude profile of percussive instruments. To implement an exponential envelope in continuous time, we would use a function like e to the minus t over tau, where tau is defined to be our time constant. The larger the value of tau, the slower the decay. And notice that as t gets larger, the value gets asymptotically smaller, but never precisely reaches zero. Another mathematically equivalent form of the exponential envelope is a to the minus t, where the value of a can be calculated as e to the 1 over tau. We went through these equations so that we could implement the exponential envelope in discrete time. We decided that we could calculate samples of v of t every single time, but that it would be quite inefficient to do so because we would need to run an exponential function each audio frame. This involves potentially a large number of multiplies for our CPU. A better approach was to use a recursive formula where the current output is equal to the previous output times some value b. B is going to be a number between 0 and 1, which causes the envelope to decay slowly over time. What we needed to do was to find the value of b such that v of n was a sampled version of the continuous time signal v of t is equal to a to the power of minus t. To do this, we needed one more thing, and that was the sample rate. Given this information, we could grind some algebra and come up with the following expression. B is equal to e to the minus 1 over tau to the power of 1 over the sample rate. The values of b that come out of this expression will always be less than 1. For example, with a time constant of 0.5 and a sample rate of 1000 Hertz, we end up with b is equal to 0.998. We saw in Lecture 12 that we could very rapidly run out of numerical precision holding this value of b if it became very close to 1. For that reason, it can sometimes be useful to use a double rather than a float to do the calculations of the exponential envelope. On some hardware, including on Bela, this is slightly less efficient than doing a float, but the precision is worth it in this case. To make an ADSR out of exponential segments, we need to take a few extra steps. First of all, we'll need some segments which gradually approach values other than 0. How do we do this? If we want the exponential envelope to start at y1 and gradually approach the value y2, what we want to do is separate the signal into two different components. Here, the value y of n is the final output of the envelope. The value v of n is going to be the simplified exponential envelope which approaches a value of 0. In other words, what we're going to do is we're going to start by defining the value v of 0 to be y1 minus y2. In other words, how far does the envelope have to move to get from its starting value to its ending value? We can then recursively define v of n as we did in the previous slide. It's equal to b times v of n minus 1, exactly as before. Then, to calculate our final output, we are going to add an offset y2 to v of n. So we have y of n is equal to y2 plus v of n. What this results in is an envelope that starts at a value of y1 at n is equal to 0, and then gradually approaches the value y2 as n goes toward infinity. The same thing applies if we want our segment to be rising rather than falling. The equations here are exactly the same, except now y1 minus y2 is a negative number rather than a positive number, such that when v of n decays toward 0, the value of y increases rather than decreases. Now we have a potential problem here, which is that an exponential envelope never actually reaches its endpoint. It only asymptotically approaches it. This could be a real problem if we want to know when our segment is finished inside of an ADSR. And it could be especially problematic inside of the attack state, where we don't want a shape that looks like this, where we have a long asymptotic approach to a value of 1 before we can move on to the decay state. There are a number of ways of approaching this problem, but our solution will be to have each segment overshoot its target value. So for example, if we wanted the segment to get to a value of 1.0, then our exponential function y of n should ultimately aim for a target higher than 1, such that we can switch states when the value crosses 1. How much overshoot should we introduce to make this work? The general rule is that the larger the overshoot, the more linear the resulting segment, as I think you can see by imagining putting that dotted blue line at different places along the segment. For the attack state, let's take an overshoot ratio of 1%. We'll have y of n asymptotically approach a value of 1.01, and when we cross a value of 1.0, we'll move from the attack to the decay state. In the decay and release segments, strictly speaking, we wouldn't necessarily need an overshoot at all. The reason for that is that neither the decay nor the release states ever, strictly speaking, needs to end in an ADSR envelope. We could just have the decay state continue, asymptotically approaching the sustain level, until we got a note off message and moved to the release state. Likewise, we could remain in the release state indefinitely, asymptotically approaching a value of 0, until we got another note onset and went back to the attack state. There is, however, a subtle efficiency advantage to having these segments have an end. And this has to do with the way the exponential value v of n is stored. V of n will be stored inside a float or a double value, where it's going to become progressively smaller every single frame. Eventually, its value will become so close to 0 that it will be smaller than the smallest available exponent to represent it in a 32 or 64-bit value. What happens then is that v of n becomes something called a d-normal number, where it's represented in a slightly different form as a float or a double. It's not something that you ever see directly as a programmer, but it's more work for the hardware to implement, and you'll find that some kinds of hardware are slower to calculate things with d-normals, where other types of hardware, for example the Neon processor on Bela, doesn't implement d-normals at all. The safe bet, therefore, is to try to avoid having your code involve d-normals at all. The way we do this is simply by having the segment end before v of n is ever going to get so small that it would be represented that way. We're now going to implement the ADSR with exponential segments rather than linear ones. To do that, we're going to create a new class called Exponential Segment, which we're going to use to replace the ramp object within ADSR. We're going to have Exponential Segment maintain all the same methods as ramp, such that later on we could use it to explore class inheritance, which is a concept we won't cover more today. One important difference between ramp and exponential segment will be the calculations that happen inside the process method. Another difference will be that we're going to have to calculate internal time constants for our exponential segments based on our overall expected length. For example, if we had a segment with a 1% overshoot, which we wanted to cross the value of 1.0 after t seconds, we need to calculate the time constant tau to ensure that it's moving at the correct speed. How do we do this? We can write out the formula y of t is equal to 1.01, that's our asymptotic value including the overshoot, 1.01 times the expression 1 minus e to the minus capital T over tau, and we set that equal to 1.0. In other words, what we're saying here is that when the time is equal to capital T, the value of y of t should be 1.0. Now we can rearrange the equation, and we can say that e to the minus t over tau should be 1 minus 1.0 divided by 1.01. Doing a bit of further algebra, we can come up with a value of tau as follows, which is calculated based on the segment length and the overshoot factor. With this particular set of values, that works out to tau is about equal to 0.22 times the length of the segment. Now we can move that calculation back into discrete time using the formula we saw before to give us a value of b. We then implement the exponential envelope using the equations we saw before. Notice here we have v of n is equal to b times v of n minus 1. In other words, we are recursively multiplying the value v of n by some value b that we have calculated based on all of the preceding formulas. That brings us then to the final task of the lecture. In the same example that you previously worked on, called ADSR class, create the exponential segment class. This is a bigger project than the previous tasks because you're going to need to define the new class for yourself in 2 new files. You should use ramp as your example for this, implementing all of the same methods inside exponential segment. However, the implementation of the methods may differ, especially in the process and the ramp2 methods. You'll also need to provide an extra argument to the ramp2 method which specifies the overshoot ratio, which is to say how far beyond the target value do you want to go. Here again are the equations we saw before for calculating the time constants and for implementing the exponential segment. R here is defined as the overshoot ratio. I recommend using a value of 1.01 for the attack segment and 1.001 or 1/10% for the decay and release segments, but you may experiment with different values. Your exponential segment class will also need some new instance variables. These include v of n, which is the value of the decaying exponential component, b, which is the multiplier that you multiply v of n by each frame. That's going to be calculated when you call the ramp2 method. You'll need the value of y2, which is the asymptote of the segment, including the value of the overshoot. And then you're also going to need to save the target value of the segment, which is the point at which the segment should end and the ADSR class will transition to the next state. Now, once you've created the exponential segment class, don't forget to update your ADSR to use it. You should be able to see now in the Bela oscilloscope that your segments are now exponential rather than linear, and I think you'll find that the sound quality, especially in the release, is a little bit better than before. Pause the video here and try this. Okay, so here we are in the exponential ADSR example, and you can see that we've created a new file called exponential-segment.h. This is very much like ramp.h, but implements exponential rather than linear segments. So we have the name of the class, which has been changed to exponential segment, and you can see that we also need to change the name of the constructors and also of the destructor. Inside of here, we otherwise have the same methods that we had inside of ramp, setting the sample rate, setting a value. Notice that inside of the method called ramp2, we have added a third argument. This argument is called overshoot ratio, implementing the amount of overshoot as we discussed in the slides. And take a look at this syntax here. This is a way in C++ of defining a default value for an argument. So we can call ramp2 with either 2 or 3 arguments. If we call it with only 2 arguments, then overshoot ratio is going to have a default value of 1.001. And then again, we have the methods for process and for telling whether the segment is finished or not. Down here at the bottom, we have a different set of instance variables compared to the ramp class. We store the sample rate, as before. We also store the current value of the segment. We store what value we're targeting, which is to say at which value we move on to the next segment. The asymptote value stores where the exponential segment would get to if we let it run for an arbitrarily long period of time. Again, the idea is that once we reach the target value, the segment will be declared to be finished, and then our ADSR will go on to the next segment. This value is going to hold only the decaying exponential component of the segment. That is to say v of n in the equations we saw in the slides. And then finally, multiplier is the value b that we saw in the slides. This is what we multiply x value by each successive frame to cause it to decay exponentially. We can go over to the implementation of this and have a look. First of all, we have our constructors, which are very similar to before. One of them specifies a sample rate. We have a method for setting the sample rate, all of this very similar to before. The setValue method does the same thing it did before, although we have to work with different instance variables. So you can see that we're setting the current value equal to our new value, and we're also setting the asymptote and the target value equal to that, setting the exp value equal to 0. The effect of all of this will be to cause the segment to hold at this constant value. Now this method, ramp2, is a little bit more complex. First of all, notice that the argument overshoot ratio no longer has the default value specified. In C++, the default value is only specified where the method is declared inside of the class. It's not specified again in the implementation. Inside of this method, the first thing that we do is we set the target value equal to the value we want to ramp to. To reiterate, the target value is the point at which we declare the segment to be finished. However, there is actually an overshoot component of this exponential segment, and calculating that is a little bit tricky. What we have to do here is we have to calculate how far we would need to go to get from where we are right now in current value to where we want to get to in the target value. We're going to save that in a local variable called distance to target. For example, if we were going from a value of 0 to a value of 1, distance to target would be equal to 1. But if we were starting from a value of 0.5, then distance to target would only be equal to 0.5. Next, we can calculate the asymptote value, which reflects the amount of overshoot. So the asymptote value is going to be equal to where we are right now, plus the distance we want to travel, times the overshoot ratio. What this says is that we actually want to travel a little bit farther than we ought to, such that we're going to overshoot the target, and then once we reach the target, we can declare the segment to be finished. Finally, we can calculate our v of n, the decaying exponential component, as the current value minus where we're going to, the asymptote value. This effectively implements the equation that we saw on the slides. From there, we can go through and implement the other equations in the slides, calculating the time constant that we need to reach the target. Notice here that the log function in C++ actually implements the natural log and not log base 10. And then from there, we calculate the multiplier, which we're going to multiply x value by each successive frame. Next, we have the process method. The process method is relatively simpler. We're going to calculate the output as the asymptote value that we want to approach, plus the decaying exponential component. The idea being that as this component decays to 0, we gradually reach this asymptote. Then we check whether the segment is finished or not. If it hasn't finished, then we continue to make this component decay according to the multiplier ratio. We return the current value back to our caller. In the finished method, we need to check whether the current value is going upwards or downwards. If the current value is going up, then we need to check whether it has gone above the target value. On the other hand, if the current value is going down, we need to see if it has gone below the target value. In either case, we would return true to say that the segment is done. Otherwise, we return false. So let's jump over to the ADSR class now and see what we need to change. Notice that instead of including ramp.h, we now need to include exponential segment.h. And down at the bottom, we are going to include an exponential segment object rather than a ramp object. Otherwise, not a whole lot is going to change in the declaration of the ADSR class. In its implementation, we can go over here and we can see in the trigger method that if we want to ramp to a value of 1.0 for the attack time, I've given it an overshoot value of 1.01. That means we're going to go 1% higher than the target. On the other hand, when I'm calling the release method, I don't actually provide that third argument. The default argument will mean that we pass it 1.001 or a 0.1% overshoot for the release. And that in fact is the same thing for the decay ramp. So actually there haven't been a whole lot of changes in the ADSR code. Almost all of it was in that new class called Exponential Segment, with only a couple changes inside of ADSR to support it. Likewise, there are hardly any changes needed in render.cpp at all. We can see that actually we have two ADSR objects just like we did before. We have all the same sliders as before, and pretty much all of this works exactly as it did before because we've changed the implementation of the ADSR class and it lets us use it in exactly the same way. So we can run this now and see how it works. If we go over to the oscilloscope now, I've already got the controls of the scope set so that we can visualize the entire envelope. Let's turn that off, and now when I press the button, you can see that we have exponential segments rather than linear ones. And we can go over and we can change some of the parameters. So again, let's drop the frequency a bit. Let's turn the attack for the amplitude fairly short. I don't know, maybe a shorter decay to higher level. How about a long release time for the amplitude so that we can really hear it sounding better than before? We'll set the filter frequency maybe to be let's say a bit more sensitive than before, maybe with a higher Q. Set the attack time to be a little slower, decay time a bit slower, and how about lower sustain level and a higher release time. Let's see what that sounds like. We can go back over here. And there we are. So we've seen here that we can implement an ADSR either with linear segments or with exponential segments. As an exercise to try on your own, you could also work out how to combine linear and exponential segments for different parts of the envelope. That brings us to the end of this lecture. We've got a number of exciting lectures following this one. To stay tuned to that, don't forget to subscribe to our YouTube channel. You can also follow us on social media at Bela Platform. You can drop by our forum for any questions or support, or you can check out some projects made with Bela on our Bela blog. Finally, you can look at the knowledge base for lots of useful information about building projects with Bela. Thanks again for following along, and we'll see you the next time.